When you use an everyday electrical device, whether it's a high-powered flashlight or a simple battery-driven clock, the charge flows in a steady, highly predictable manner. In 1828, George Simon Ohm formalized this behavior. He observed a simple, linear relationship where the voltage across a conductor dictates the current, constrained by a constant value we now call resistance. But if we zoom into the microscopic scale of the wire, classical Newtonian physics presents an immediate contradiction. An isolated electron exposed to an electric field doesn't travel at a steady speed, it accelerates. The applied electric field exerts a continuous force on the electron. According to basic electrostatics, this force equals the electron's charge times the electric field. And as Newton established, that force must also equal the particle's mass times its acceleration. By rearranging the formula to solve for acceleration, we get A equals negative E times E over m. Because the charge of an electron, the electric field, and the mass are all fixed constants, the acceleration of the electron must also be constant. This graph illustrates the problem. If the acceleration is constant, the velocity of the electrons, and therefore the rate of charge flowing through the wire, should increase exponentially over time. Yet macroscopic current, represented by this flat horizontal line, is demonstrably steady. For our macroscopic measurements to make sense, the electrons inside the conductor must be experiencing a continuous opposing force that prevents them from accelerating indefinitely. Left strictly to the forces of nature, electric charge doesn't naturally flow in a steady state. A lightning strike transfers tens of thousands of amperes from the clouds to the earth in a chaotic, fluctuating burst. The steady, reliable current we rely on is an engineered condition. By routing power through solid metallic conductors, we force a smooth, linear relationship between voltage and current. When you close a circuit, power seems to arrive instantly. This creates a powerful illusion that the electrons themselves are racing from the battery to the device at high speeds. In reality, it is the electric field that propagates through the circuit, moving at nearly the speed of light, roughly 300 million meters per second. The physical electrons themselves do not move at anything close to that speed. In a typical copper wire carrying 1.5 amps, the average drift velocity of the electrons is barely a millimeter per second. Electricity is not a frictionless river of particles. The power in a circuit comes from a near instantaneous electromagnetic signal that initiates a slow, heavily interrupted physical crawl. To understand this interrupted crawl, we have to look at the baseline state of a conductor when no external electric field is applied. Inside a solid metal, free electrons bounce between the heavy, tightly packed positive ions of the lattice. Driven by thermal energy, these electrons travel at immense speeds, often hundreds of thousands of meters per second. But because they collide continuously and rebound in random directions, their average directional velocity is zero. When an external electric field is applied, it exerts a uniform pull on the system. Now, between each collision, the electron's previously straight path curves slightly, creating a tiny bias in the direction opposite to the electric field. The electron only manages to accelerate during the microscopic windows of free flight. Every time it strikes a heavy positive ion, its velocity is scrambled and its forward momentum is reset. We quantify this stop-and-go cycle using a variable called relaxation time, denoted by the Greek letter tau. This is the average time interval an electron spends flying through the empty space before striking the next ion. Because of this continuous resetting, the overall drift velocity of the electron across the wire is its constant acceleration multiplied by this average relaxation time. The metallic lattice acts as a continuous physical brake. By interrupting the electron's flight millions of times a second, the lattice caps the speed, converting exponential acceleration into a steady average drift. We can scale this single particle mechanic up to calculate the total current of an entire wire. We start by isolating a specific cross-sectional area of the conductor, labeled A. Macroscopic current, represented by I, is defined mathematically as the total net charge crossing this specific area during a given time interval. To find that total charge, we isolate a subvolume of the wire. The length of this cylinder is the electron drift velocity multiplied by the time interval. Every single free electron inside this volume will cross the plane A before the time interval expires. We calculate the total charge of this cylinder by taking its volume and multiplying it by the charge of a single electron, E, and then by N, the number density of free electrons in that specific metal. To find the current, we divide our total charge equation by the time interval. The time variables cancel out, leaving us with I equals NEA times the drift velocity. This equation allows us to link the microscopic, statistical crawl of individual particles to the measurable flow of current we observe in any macroscopic circuit. With our macroscopic current equation and our microscopic drift velocity equation established, we can mathematically derive Ohm's law from first principles. By substituting the microscopic equation for drift velocity directly into the macroscopic current equation, the terms expand, exposing the physical components of the flow. Inside this expression, we have the charge and mass of an electron, alongside the carrier density n and the relaxation time tau. Because these variables are dictated by the structural properties of the material, we group them together under a single constant, conductivity, represented by sigma. By replacing that complex bracket with sigma, we arrive at the vector form of Ohm's law. Current density equals conductivity times the electric field. If we convert current density back to total current over area and the electric field back to voltage over length, the equation perfectly rearranges into the classic formula, V equals I times R. Ohm's law is a statistical result. The resistance of any wire is dictated by its macroscopic geometry and the collision frequency of its atomic lattice. Because resistance hides these microscopic variables inside a single letter, it is vulnerable to environmental changes, most notably heat. The mass and charge of an electron are fixed. The only variables within conductivity that can change are the density of the charge carriers and the relaxation time between collisions. This chart plots electrical resistivity against temperature. Notice the steady upward slope for copper. As the metal heats up, its atomic lattice vibrates more aggressively, increasing the frequency of collisions and shrinking the relaxation time. Now look at the second curve added to the chart, representing a typical semiconductor. Here, resistivity sharply plummets as the temperature rises. While heating a semiconductor also increases collisions, the thermal energy simultaneously breaks atomic bonds. This frees massive numbers of new charge carriers. In semiconductors, that surge in carrier density overpowers the drop in relaxation time. By dissecting resistance into its atomic components, we can predict exactly how a material will fail under stress, or use these microscopic variables to engineer new technologies at the nanometer scale.